thanks for joining me today. My name is Ilya Tyagin, and I'm a PhD candidate in bioinformatics data science at the University of Delaware. It is my pleasure to introduce you our latest work, Dyport, which stands for Dynamic Importance-Based Biomedical Hypothesis Generation Benchmarking Technique. Hypothesis generation systems are useful, but hard to validate, because the goal is to find novel information that is unknown to even people behind designing such systems. End-to-end frameworks may incorporate textual data or focus on experimental databases, but it is not that common to find anything utilizing both, because connections between literature and databases are often missing. Moreover, biomedical databases and systems based on different data sources may incorporate multiple ID standards, which makes their comparison even more difficult. At the end, we are interested in what actually made it to experimental databases, even if hypothesis generation systems were trained exclusively on text mining data. To address these challenges, we proposed a benchmarking framework called Dyport, which leverages both textual and biocurated databases. We connect concepts and their associations from databases to the corresponding literature from PubMed. Moreover, our system is dynamic by design. It supports arbitrary time slicing to benchmark already existing systems. We do not enforce the training to be performed on our dataset. Now, let's briefly describe the system and its components. We have two starting points: a list of biocurated databases and midline abstracts. For databases, we perform parsing and ID mapping. We transform all entity IDs into UMLS concept identifiers and merge similar concepts from different databases together. For text, we perform named entity recognition and concept normalization. We also extract all pairwise concept occurrences on a document or abstract level. To connect experimental databases and textual sources, we simply find an intersection between associations obtained from these two sources, which results in a list in orange box. Then we created a dynamic network. Each association between two concepts is treated like an edge in the network and has a timestamp. Therefore, we create a graph from biomedical concepts as nodes and their associations as edges, added over time according to their occurrences in literature. After that, we apply a range of methods to get the importance of associations in the network. Some of them are network-based, like centrality metrics, and some of them are used to interpret machine learning models, like attribution. The last step is to use the obtained connections and their importance scores, if applicable, to benchmark hypothesis generation systems. This is how the data is obtained. We combine biomedical concept associations from biocurated databases, which are listed in the table on the right, and scientific abstracts from Medline. Then we perform cross-referencing, which leaves us with a set of high-quality concept associations that we can track over time and predict with multiple hypothesis generation systems. Dyport enables us to perform hypothesis generation benchmarking with flexibility usually unavailable to other methods. We call it stratification-based benchmarking. Our framework incorporates importance, temporal, and semantic information, which is helpful to identify trends in models' behavior and compare them under different evaluation protocols. Let's start with importance-based benchmarking, which is the main contribution of our work. Importance I is a compound measure calculated for all newly introduced concept associations at a timestamp t, describing their role in the knowledge dynamics. We perform look-ahead and look-behind analysis of the connections, which is shown on the timeline on the right. The list of importance components consists of multiple elements and takes into account attribution, network, and citation information. The importance I is calculated as average percentile rank of its individual components for every association E. Once the importance scores are calculated, we can split all the connections into a number of bins. In this example, we have 3 bins with low, medium, and high importance, and run the evaluation separately for every bin. We can see that the more important or impactful associations are, the harder it is to predict them correctly. Temporal stratification shows how predictive performance for all systems gradually drops over time. Here, we trained all models on the same Medline snapshot from 2015 and repeatedly evaluated them on the novel associations introduced at each subsequent year, starting from 2016. Semantic stratification allows us to compare hypothesis generation systems with respect to different target domains represented by their corresponding semantic types. From this experiment, we can see, for example, that chemical interactions are easier to predict than gene interactions, which is true for all systems. This concludes my short presentation. If you have any questions, please feel free to contact us. You can find reference information on this slide. Thank you for your attention.